All right, welcome back to a very important segment in this course, and we are looking at a statistical test or analysis. Basically, focus on parametric test first. Um, and that is topic that statistical test. Statistical analysis in R actually refers to the process of using R and its extensive collection of statistical libraries to analyze data. R is full of libraries statistically, and this perform statistical tests and make inferences from data. It's a powerful tool due to its rich ecosystem of packages designed specifically for statistical modeling, data visualization, and hypothesis testing. This statistical analysis actually in how typically involves the following steps. It involves data importing and cleaning, which we call data wrangling. We have done that before. It also involves EDA, exploratory data analysis. Also involves descriptive statistics, which looking at the characteristic of data, chart and graph, calculating the mean, the mode, and the median. Right. It also involves statistical modeling, and also involve hypothesis testing and model evaluation and the interpretation and reporting. So this is a full package actually for statistical analysis. But now we are cover some of this stuff in the past, so we want to focus on parametric testing. I thought us before we can look at parametric testing, you should understand that there are three basic assumptions. Three basic assumptions. Majority of our data that we use in a research, majority of them, they don't usually fall into these parametric rules, under the parametric rules. They don't usually fall into, some of them are not parametric compliant. Okay, so usually in science, medical research, or biomedical research, they fall into non-parametric testing. All right, so because there are three rules or assumptions that you must be able to pass for you to use parametric testing. The first one is the data must be large enough, the sample size must be large enough to do the experiment. That's number one. And luckily, our data we are able to be using today has a large size. All right. Number two is that your non your the data must be normally distributed. You must pass the test of normal distribution. Okay, and that's number two. And number three is that homogeneity of variance. Okay, it must be homogeneously variance, which means that the variance based on the standard deviation must be equal, must be balanced. So these three rules are very important, and there are tests for them to actually validate if they are accurate or not. If your data is valid or passes the test or not, before you can proceed to what is called parametric test. So you have to first bring in your data and then run analysis on this, both graphically and numerically, to confirm if your data passes the test. Then you can go ahead with parametric test. But if you fail the test, then you have to switch over to non-parametric testing. All right, so let's proceed now. We want to look at of course, let's look at our library as usual. We have two libraries usually go to look at, go to load. Okay. Okay. So now we have a data set we want to use today. I call it Anima. Okay, that's our data called Anima, and the name of the Anima is called hardvac. Hardvac. Now I know that sounds very new or sometimes strange to some of us because maybe you may not be familiar with hardvac. Hardvac is an animal from Africa, especially from South Africa. Now it's not a common animal you see everywhere. That's why the name does not sound very familiar. All right, so let me show you how it looks like. This hardback. All right, it's a pig-like animal. Okay, and so you can see this is how it look like. Okay, it has a size of around 65 a kilogram. Okay, and the height around 60, maybe it's around 60 to 70. All right, so that is a when you stands up. So it's also big animal. All right, so he has only one species in the world. Artifact has only one species, even though it can be found in many islands in Africa, but it has only one species. Not like some animals, they have several species, but hardback has only one species. So, so it's not generally common everywhere that you can see, but at least you can learn something about hardback today as well as you have learned about other animals. All right, you can use any other data set that are parametric test compliance. Okay, not necessarily you must use, but I just want to use this data set as an experiment, as a sample to see how you work on those individual tests. All right, so we have already have the data set called advac underscore animal.csv in our listing, our directory, our working directory. So we just run. Don't forget, usually create a working directory before you start. I don't need to repeat that for now. Now we are now getting towards more deeper to the step. By now you are getting familiar with that method of you must have working directory first. That is where all your data are kept. Okay, you want to bring in a file, it must be from there. You want to save a file or images, it must be from there. So you must go to the place. So that you not have them here and there. So you must have a working directory. And I show you how to do that last time. You can create it by using code. You can also go to session here. Okay, go to working directory. You can set a file location or create or choose a panel play or choose a working directory. You can open here and then create one and select it. So it's very easy, very simple. So it's not difficult at all. All right, now that we have loaded our data set, so let's first attach it. I told you the reason why we are doing attach, so that we will not be using normally when you go to a data set. Okay, let me describe the data set first before we attach. Let me describe first. Okay, let's put attach under here. So let's first describe what is inside the data set called AVAC. All right. This animal, we have 4,999 rows, 4,000, almost 5,000, almost 5,000 observations. Okay, we have sufficient data. Okay, observations. Okay, now it has a gender. Okay, column. It has a age column. So the age of the animal. It has the year. Yeah, it has also uh, the weight. Okay, but the year of experiment or the year of acquisition, and they also have height, they have weight, right? And we have a island where they are located. Okay, all right. So that is basically what we have under this data set, which make the work easy for us, not too complicated. All right. Now that we have 6 columns basically. Now we understood the data structure of this particular data set, then we can attach it now. The purpose of attaching is that is normally because, like I said before, if you want to access any of these components, the elements here, you have to do dollar sign. All right. Now, if I type animal, for example, animal, I want to access age, for example, I have to type $age. Okay, you can see it's showing me now. All right, $age or gender. If I type $gender, all right. So if I run it, it will give me the gender. You can see, show me the gender, male and female, and you can see throughout. All right, so that is gender. All right, so but I don't want to be using dollar sign all the time, dollar sign all the time. I want to use directly each of the column. Okay, I want to use gender just for gender straight. I want to use a animal, or I want to use many other variables such as a year or age or height or weight or island. I just use it straight. I don't need to be calling it using $sign. All right, that's the purpose of attaching it. So if I attach it now, unless occasionally where it is needed, I just want to use it. But normally I should be able to supply my data. If I run this line of code now, so I've attached it. Okay, attach this animal called AVAP now. Okay. Don't mind all those following jet mask, 5 gender, age, and weight. Okay. I mean, that already been attached before, so never mind. I'm attaching for the second time. All right. So now let's summarize. Let's look at the summary of what this particular data contain. All right. So summary. So we have a gender, okay, character, okay. We have a age, minimum, maximum, first quarter, third quarter, median, mean, right? Which is this median mean. We have a year. Okay, this is a year to 2000 to 2002. At 3 years in range. We have height of each of the specimen. Okay, height, the height of each specimen. In the height is in centimeter. All right, we have a weight in kilogram. Right, of each of the specimen. All right, we have a island where they are located. All right, island where they are located. So these are basically our summary of this so I've seen that now is you can now go ahead and see work on our data. So the first thing you want to do a normal definition check or parametric check first, okay, to see if our data set is parametric compliant. All right, so we want to do some plotting. All right, let's do some plotting to see. Let's start with plotting first to see if the data set. So we have a height. Let's supply height first and see run height. This okay. I need to test something just now, so that's why. All right, so now if I run this line of code, I want to test for height first. I'll test for height, then I will now do the same test for weight, but possibly for age as well if I want to, right? Because we want to do this for numeric. This one they are already done for numeric data. Okay, these are continuous. Don't forget continuous data, height and weight. Okay, we want to that to be mutually focus on that two components. You can choose any one of them to run our analysis, either height or weight, right? Okay, so we want to use density plot first on the height. We run this experiment. You see, okay, you can see it in the chart here that the curve look normal. All right, you can run the Q norm, okay, which I've shown you before. You can see that it's straight here, okay. It's straight. Let's also look at this histogram. You can see histogram also. Look at how it look like. All right. You can also run the box plot as well. Box plot. You can see the box plot. Though you have some outliers. All right. Outlier does not stop you for being actually normally distributed. Outlier does not stop you. Okay. You can still have outliers. Yes, you can see normally distributed. So it does not stop it. All right. So we can further do some for example, if I let me run this line first. Let me just put this line here before I go for this. This one will be test, numerical test. So these are the graphics. Look at the graphic test first. All right. So we are still looking at this test also. Box plot. You can draw a histogram with color. Okay. You can see our mean is red. Our what they call it now, median is blue, don't forget I explained just last time when the mean is greater than median and when median is greater than mean, they have different thing. Okay, and when it is normally distributed, it means the mean and the median are equal. If I run this histogram first, okay, let's run step by step. Run this first, nothing is here. Then run the second one. Can see the red here. So this is our mean second. Then if you run the third one, can see, but the mean lies on the median, or the median lies on the mean rather. So which means equal to median. That's what it means. All right. So which means it make it normally distributed. But you cannot conclude like that. You have to also test using a statistical test, which is called Shapiro test. Okay, Shapiro test. So we supply our height. Okay, this is for age. Actually, for age. Let me put height there. I'm sorry. This is for age. So let me change to height. Height. All right. So let's run this line. Okay, this line. Okay. Okay. So that's the same thing happen. So, but you can see a little bit tiny red showing here, not like age. You can see some little tiny red showing, but it's small. But it's not. It's still okay. All right. So we can further now test another test called Shapiro test. Okay, this is for test for normality test. Okay, and then we can further test for also for variance, for homogeneity as well, which is for homogeneity of variance. So let me see. So that is for this one. So we're going to that later. So I can take this one off from here. All right. So now we want to run this now based on height. Let's see first on this line and see. Okay. So now Shapiro test, normality test is not significant. Okay. And I explained the other time that whenever it's not significant, it means that it is normally distributed. Okay. So take note of that. It must not be significant because it's less. It's not up to. Is higher than 0.05, which means that it's not significant statistically, which also means that it is normally distributed. So take note of that statement. I don't want you to forget that. Now, the same thing happens to, let's test for normality, I mean for variance now. Let's be using height here. Now we're going to supply, let's supply gender. You can use also Iceland. So, but we'll be using mostly Iceland and gender for our experiments. So, want to supply this one will be a categorical data. This one will be a continuous numeric data. So, if you run this 11 test, should be able to give us our result. If it was 0.2, don't mind the one here, okay? If it was 0.2, all right, which is not significant, which means this particular is a homogeneous of variance is valid, right? So the third rule is the amount of sample and we have enough amount of sample which is almost 5,000, which is far too much for experiment. Okay, so that makes this particular data set valid for parametric tests. All right, so let's now go further and run some tests. The first test I want us to perform is called chi-square. All right, chi-square, like I said before, could be used under non-parametric. When you use under parametric, depend on what you are working with. You are basically working because majorly what one of the valid tests, both parametric or non-parametric tests for categorical data is simply a chi-square. That is major work. So it doesn't test on numerical data. It tests only on the categorical data. It doesn't fall into a particular category. Many people call it a parametric, whilst many people call it non-parametric. But it's in between. You can use it for parametric if you want to test categorical data on the parametric. You also use it for non-parametric if you want to take categorical data. because there's no other analysis that are very valid for such at the moment. So let's uh, plot out some tables first. I mean, to see our data, our category data at a glance. So we want to first run this and say, okay, let's create an object. This variable, let's call it all Iceland. You want to see how many Iceland do we have. Then let's use function table function and supply Iceland inside it. I will have said nanimal slash dollar Iceland, but because I've already attached my variable, my data set, so I don't need to say animal slash dollar island. So I can just say island here. All right. So if I run this line of code now, I've already assigned this to all island. Okay. So if I run this also, if you have my island, we have island, 3 islands. We have a grassland, we have mountain, and we have savanna. So it also show me that in grassland we have 330 observation. In the mountain we have 2,797. In savanna we have 585. So it means we have a more on the mountain, more of the animals that they call advert on the mountain and than on other parts, and a little more on savanna. The lower sample is gotten from grassland. So that might be reason for that actually, because I think they reside more on the mountain. Okay. So and then we can also run gender here. Okay, or gender, which means table gender. We can run this line. All right. So if you run this line, also we will to know. Let's we see that how many which of them are female and male. We have 2,474 female and 2,525 male. So we can also run what is called contingency table, contingency table, which try to break down our data, our two calculated data into two. All right, we have gender in Iceland. We want to look at how many gender in each Iceland. That's what we are talking about. That is, we use a contingency table to do that. So what do we do now? We say we create an object called gender in island, then say call table function, island first, gender second. So we pass this into the table function and to see how many do we have. So if you run this line of code now, run this line of code and look at our gender in Iceland now, run this. Now it's in Iceland. We can island here, we have gender here, we have, you can see male and female. So under each island we have grassland, we have 176 female and 154 male. Under mountain we have 1356 female, and so we have more of male, more female in grassland than male. But in mountain island we have more of also male also. Now we have more of male than female, and in savanna we have more of female than male. So this is to help us to understand, okay, how our data is distributed in each location. All right. So let's now do a test on the first of chi-square test. Now, don't forget, I step by step, I stepwisely arrange each of these contents so that you can understand as we are going gradually. So the first thing is called chi-square test, and this test for one category data. We have two types we have to do here. The first one is for one category variable, which is maybe on gender or on island. The second one will be for dependent, when you are now combining more than one categorical data together, which is usually two categorical data. All right, so let's say, okay, I mean, test whether there is a meaningful difference in the proportions of various categories. We have a categories data, which is called we have island, we have gender. They are both categorical data. So can use any one of them, can use either this or this. So to test if there is any meaningful difference. Okay, maybe you can say the question is that we can come up with a question that says if there is a statistical significant difference in the proportion of the island. Looking at this now, looking at this, we see that their gender are not the same here and here, here and here, here and here. The proportion are different. So can even use the percentage as well. using probe the table function. I don't know if I can do that now. Let me see if I can use probe dot table. If I pass this, let me see, pass or underscore island. Let me see. All right, so we are looking at percentage now. All right, percentage of this one. Or let's also round it to round. Let me say round and open bracket, over table, comma 2, close bracket. Okay, let's use this method so that you can know how many we have. Okay, so we have 0. What we have here now 0.09, 0.75, and 0.16. This is just this 9%, this 75%, and this is 16%. All right. So you can multiply by 100. Actually, you can just say multiply by 100. Okay. You can multiply by 100 to see what we have there. All right. If you multiply by 100, we give us our answer. Okay. You can see what I'm saying. So 9, 25, 16%. All right. So having gotten that, we know that they have the portion of each of the categorical data. They are not the same, both for gender and for island. So, but is this statistically significant? That is our question now. I want to check. So we have a let's say we have a hypothesis developed. Okay, so we want to first calculate, is there a statistical significant difference in the proportion of the island or gender? Any one of the two, you can use any one of the two. Okay, so now the first thing, because we are dealing with only one categorical variable first, that is what you call test for proportion, which is other known as called chi-square goodness of fit. Goodness of fit test is for one categorical data. Don't forget, for one categorical data, we call it test for proportion. We want to look at the proportion of that particular category. If the spread, I mean the proportion is statistically significant. Now, if you will do that, now we want to say, okay, H naught, H, the null hypothesis says the proportion of the island are equal. So we have to set it to that one first. We have to set our null hypothesis to this first. But with this our arguments, okay, we are saying that this one but must test it. Normally that's how we set it first. Then our null hypothesis, our alternate hypothesis, HA or H1, will be the portion of the island are not equal. So we now pass it, we now run a test to see if they are equal or not. So we can now reject one or non-reject this. So let's we have already run this. Okay, we don't need to run this again. This is a all Iceland. You already have it run, which is this. Okay, this is this. So if you run this again, you can see what to give us before this. So we need it to run our analysis. Okay, so we don't need to run this anymore. So we can now test it and call it here. You can say chi-square dot test. Right, just say chi-square dot test and pass this your island into it, or gender, whichever one you want to pass to it. Just pass it to it and then run it experiment. So we run it now. It's significant. P is equal to what? 2.2 times 10 power minus 16, which means 0.00000 is far less than 0.05. Okay, so that is what we got. Okay, for our experiment. So we can also use this method also by using a piping animal. Okay, select island table chi-square. So if you run this line, also you give us the same answer. All right, so we have the same answer here. Okay, the same thing we have here. Okay, we have here. All right, so that is what we have now. So we can conclude here, and p value is equal to this, which means proportion are if the proportion were equal, the probability of the same input data providing a difference of this magnitude or more is less than 0.0. Therefore, reject H naught. Reject that the proportion are equal, which is evidence that the proportion are not equal. All right, so evidence by what? Not by merely assuming, but by test. Okay, We have checked, we have confirmed that they are not equal, but we have to test to conclude. That's what we did just for chi-square now. So we have to test to conclude that, oh, truly they are not equal. All right, so you can do the same thing for gender as well, to test if the portion of gender is equal to. You can just supply gender here. Don't forget that we have done this also here. Okay, so you can put all gender here also to test if they are equal or not. So let's just try and put gender under chi-square here and say all that's for gender and run the experiment. So you can see, even though in our observation we saw that the gender are not equal, but in our experiment it's not so. That is what you must understand about experiments. That's why you must test. You are saying that the proportion percentage are different, okay, but statistically speaking, they are not the same. They are not significant. So what I'm saying is that the proportion of the gender are equal. The proportion of gender for alternative they are not equal. So, but experiments show that they are not equal because this one is greater than 0.05. So that is how you have to declare your data, because don't just observe and declare by just looking at the data. You must test to verify, because the only way you can verify is by testing, not by just looking at it and giving us answer. All right, so that is that about that. So the second part is to use two categorical variables. Okay, so that has become the test to determine whether there is a relationship between two categorical variables. Okay, we have two categorical variables under this experiment, under this particular data set. We have gender and we have island. All right, island is where we get each of these animals, and also we also have gender. Okay, we have different gender in different island, which we saw in our table just now, contingency table. So let's see, we know what they call test of independence. So question, is there any relationship between the island and gender? Which means there is no, you can say that H, I mean, there is no relationship between the two variables. The variables are independent. That's what it means. They are not dependent. That is H naught. Then, because knowing the value of one variable does not help to predict the value of the other variable. That's what it means. They are not. They are independent. Knowing one value of variable does not help to predict the other. And then number the other one say there is a relationship between the two variables. The variable are dependent. That is our second this alternative hypothesis right now. That is to say, knowing the value of one variable does help to predict the value of the other. So we want to test now how true it is. So we can now use our gender in Iceland. Now we have island, we have gender here. All right, so we pass it to the chi-square to test. So it's called test of independence. Now that's what we are doing now. We have done for proportion, which is a goodness of fit. So we are doing for dependent now. So we can run this line now. If you run this line now on chi-square to give us our result, right? Object. Okay, sorry. I didn't run this. Let me run this first. All right, so let me run this. All right, so this is nearly significant, nearly, but not exactly 0.05. But so we cannot say this one is not significant because 0.058 is greater than 0.05. So it means it's not significant, which means that we have to reject. Don't forget we have to hypothesis here now. Say there is a this show that there is no relationship. That's what it means. There's no relationship between the two variables. So we have to reject the hypothesis in the favor of a null hypothesis. Okay, so you understand that? So that is exactly how you do experiment. You have to reject this, that there is a relationship between two variables, that the variables are dependent. You have to reject because it's not significant, even though it's nearly, but not significant. So we have to, we do not reject null hypothesis that says that the relationship between the variables are independent. So we only reject all the alternative hypotheses that say that the relationship between the two are dependent, that the variables are dependent, but the variables are not dependent because it's not significant. Okay, so that is method behind it. That is under chi-square. Based on this frequency or percentages, we should not expect a strong relationship between island and we should not expect relationship between them, okay, and gender, okay. The value of the chi-square is 5.67, which we got here, okay. This 5.67 now approximately, and the p-value is practically 0.059. So we do not reject the null hypothesis of the no relationship. There was no significant relationship between the island and gender. So that is just our conclusion. All right. So we can now go further to t-test now. T-test. All right. So after the t-test now, I will stop. Then we can continue the rest of the test in second part. So t-test, we have categories of t-test actually. We have a single sample t-test. Right. That is one numeric variable. For example, you have to test one numeric variable, single sample t-test. So this to compare the mean of a sample with a known reference. A known reference mean, okay? You have a known reference mean, which means you have a value you are trying to, you have already set, okay, as a reference mean. So for example, now maybe you have a list of a number of heights or weight of the animals, and they want to compare the mean of the animals, of the weight of the or the height of the animal or the age. So you can set a particular known reference that you already know before. Just set, okay, I know that the mean of this, the average of this age is maybe 50 or 60. But is this your 60 that you set? Is it significant? You have to test. So we are using what is called single sample t-test. Let's have a question. Okay, is the mean weight of the AVAC of the hardvac is mountain Iceland equal to 0? Do they have equal mean? Okay, so that is the default is 0 is default. Okay, that means equal mean. Or if you set to a particular value 70 or 60 or 50, whichever value you want to set to, if we set our mu, so this is called mu, is our reference mean. We are going to see that later, to a reference mean. So we can now test against it to see if it's equal or not. That is what is the simple test is talking about, simple test. So the mean, let's say we have h naught, which means our h not hypothesis, the mean weight of the aardvark in mountain Iceland is 70. So we are not even looking at all the islands. We just want to check on the mountain island only. Is 70. Okay, you can say, okay, our alternative say the mean weight of the aardvark in mountain is not 70. So we want to test against, we want to see if what we are saying is correct or not. So we can use a piping here because we want to select, we want to filter by mountain Iceland. You can actually just test directly without using just test all of them. Okay, okay, and just apply all of them. You can remove this filter and just test all of them. Test the weight of all the animals to see if their average is 70. Okay, or if it's against our reference mean we supply. All right, so that is what we are looking at. But we want to filter, we want to look at only on mountain island. We can look at other mountain, maybe you go to grassland or savannah, depend on, you can just test. So I will make this particular data set available for you to use to test your experiments. Okay, so you can download it and use for your experiments. Okay, so now looking at this, now we can run this experiment and first run. I can first run this line together. I can run this line first, but I can run together to see what you are talking about. So let's try and run this now. And then, because we assign this line, we assign it to a variable called t-test, so we can run this separately. Now, let's see. So our first photo, let's start from this down here. Our mean is 64.69, which is not 70. So it's against our mu we set as a reference mean here. Okay, so now our p-value is significant. Alternative hypothesis, true mean is not equal to 70. Okay, so this is our lower bound, upper bound interval. Over the interval, we have a that is 95%, but we have lower bound, upper bound. Right, so when we have estimate of 64.69, which is not 70. Okay, so what do? We have to reject that. We have to reject uh, the non hypothesis that our mean value is 70. Have to reject. All right, in the favor of alternate hypothesis that the minimum value is not 70. Okay, so that's what we do. We reject that. All right, so you can also check, okay, average weight of all animals here. Okay, to test animal. So if for all now, this for all. We are not doing for only for mountain again. So just for all, like I said before, and we are setting our mean, our MU, which reference mean to 70. So if we test this, run this line, okay, we have 64.67, different from the former one, just a little bit different, okay, and it's still significant, okay, which means it's not equal to 0 and it's not equal to 70, which means that normally it's supposed to be equal to 0. What do we use 0? If we don't supply this now, okay, just close our bracket here. You know reference mean, it means it's taking the default value of 0, all right, which means they are equal. But because we are setting the reference mean, so that's why we use this. Okay, so we could have just close this, okay, remove this, okay, and close it here, so that we just have a default value of 0. So which means equal variance, equal mean. That's what it means. All right, so it is indeed significant, higher than 70, higher than 70. All right, you could report, you got this as follow, and say that the average weight of the Avak mountain island is mean 64.69. Standard deviation is we can find standard deviation as well, actually as well. So SD, you can find SD. So but I don't, let's continue. So I already found that given us 1.05. So we significant below 70. So our T equals to our T is equal to minus T of 2750, which means degree of freedom is equal to 1 minus 264.82. P less than, so you don't to say P equal to 2.20. No, just say P less than 0.01001. That is how you declare the port. P less than 0.001. So you don't to write P equals to 2.20000. No, don't need to do that. So that is that. So we also have what they call independent test, sample test. It is test, it's unpaired, okay, unpaired sample test. So it basically work with one numerical and one categorical data. It is two sample tests. All right. So this means to divide. This is to compare the mean of two independent groups. This is not two categorical variable groups. No, in the categorical variable you can have two groups and more than two groups. For example, now gender is two, so basically it's two groups. Okay, and the island is more than two groups. Gender is, we have male, we have female. That's two groups. Take note of that. That's in groups and the categorical. So in categorical we have two groups, but in the island we have three groups. We have a savanna, we have a grassland, and we have mountain. Three groups. So which is more than two. So I want to test for one numeric now and one category. So this numeric must be continuous numerical variable like height, weight, and so and other like that. So we want to compare the two groups. So we want to test whether male and female halfback differ in the degree to which they are weighted. When you weight one, okay, male, if you weigh male, is it the same or equal to when you weigh female? So let's create a box plots first. We want to create a box plots first and check the mean and the deviation and SD of gender. So we can see box plots here. This female, this male. You can see the mean here, and they're not the same. Okay. So let's we can now run experiment here. Let's run experiment here and fine. What you want to do? Let's create an object here. our animal is called here. We're piping now. So we want to group it by gender. Okay, I want to go by gender. We now summarize. Okay, find the mean weight of each gender. Okay, the mean equal to mean weight. The SD means standard deviation of gender. Okay, we find here. So let's run this experiment now. Oh, I want to run. Let's run the first 5. Okay, let's run everything because we already summarized. So if you run this now, because we are assigned, we just run this now. Can you see now? Gender, we have female and male. We have mean weight 64.3. This one 65.0. The mean weight you can see here. You can see this one 64.3. This one 65.0 for female, and the SD is 0.992 and 0.997. You can see the SD is somehow very close. So now it shows here that the male weight slightly higher than female. Okay, male 65.4 higher than female. All right. But we want to know whether this difference is significant. Okay, want to know. Okay, so an independent sample t-test can provide the answer. The male and the female in our experiment are the independent samples now. So the independent sample are the male and the female, okay? But we need to check an assumption first that the variance of the two independent samples are equal. So we use what they call car library. So though we should have done that first. No, we have done that. We have done that already. This is called level test, weight and gender. We have done that. So don't to repeat that again. So you can go ahead and do that by yourself, okay? So they are equal. So we can go ahead with our tests. All right. So we want to now test whether the mean differ between genders. That's what we are trying to do now. Whether the mean differ between genders. So the mean weight differ between genders. So if you run the t-test now, we have weight to gender, variance equal to true. This is our line of experiment. Okay, so we want to test this is called pair, you call unpair. Okay, so we call it's called unpair. All right. We are under so this we unpair sample t-test is called independent test. All right, so we have one numerical continuous variable and we have one categorical variable. So our non-numerical continuous variable is called a weight. Our categorical variable is called gender. This is between two groups now. Don't forget two groups because these have two groups inside, male and female. So we have a variance equal to equal. For this one should be false for non-equal variable. Okay. So when you run this experiment now, we want to check. We have it's significant here. Okay, I need to hypothesis say true difference in mean between group female and group male is not equal to 0. So this is lower bound, upper bound, and we have a mean group equal 64.32 and we have 65.03. So you can see that they are not equal. So this is the mean for female, the mean for male. They are not equal here. So in the experiment, so we could report this as follows: male equals to 65, SD equals to 0.99 from what you got. So and the female equals to this and male equals to this differ in degree to which they are weighted. So which means that which is T3 for our degree of freedom here. Can pass like this. This is how you report in manuscript or your thesis. The minus 25 is our T we got. Then P is less than 0.01. Okay, less than 0.001. So this is how you report the experiment. Okay, so that is testing for what do you call it? So we also have for pair t-test. So let's call dependent sample t-test now, which means that the dependent sample t-test pair t-test is used to compare the mean of two rated groups now, two groups that are related, one numeric and one pair. Okay, so one numeric and one pair, so two rated groups. So let's assume that you want to compare the weight of animals between two different islands. For example, the animal on the mountain, animal on the island. All right. So is that mean difference between the pair of weight of AVAC, mountain, island, and the Savannah Island. Is there any? So just we have let's assume we have a H naught. Our naught of this is the mean difference between the pairs way of island in mountain and the in Savannah is 0. You should no mean difference. Or we can say that the mean for the second question, the mean for our alternative now, the mean difference for the island is not equal to 0. There's a difference. So we have to select now, because when you are dealing with this sort of test, they must come to different, they might have the same observation, because we want to, they must have the same observation. But when you look at our data, the mountain and Savannah have not the same, they don't have the same observation, which means you tested for example, this particular does not actually support our test actually, but you want to use it to run the test so that you can see a sample, right? Maybe you tested a patient this month or this week, and you test the same set of patients next week. Want to compare to do that is what we are talking about, all right? That's what I'm talking about. We want to test the two based on the drug maybe administered to them. Want to test them. So when you test this patient today, you record it. Next week also you tested the patient, you record it, and based on the drug administered, you want to compare. That is what we are doing. So, but we are using the two mountains now to do our experiment, because we don't have that kind of data available. So we use two mountains, maybe on Savannah on the mountain. I mean on two island. Okay, we select two islands on Savannah or on the mountain. So we've got to filter first to make the data our observation equal. Okay, we filter first. Okay, you select the from Savannah first and select from mountain also, mountain for mountain first and Savannah also. So want to look at the length of equal, not, but the length is not equal actually. Okay, if you run this experiment now, if you run this line, you see that they are not equal in length. One is more than the other. So we set a seed now to set. We set a seed. Let's run this line of code first. Let's run this line of code. All right. So we are filtered. So we can run the length if you want to run the length. So let's set a seed. Okay, for the positivity only. So we can now set the number of lengths. Want to make sure the length is rhyme, not the same length. That's what we're trying to do here now. We run this line. So the length we select the length, the same length, equal length for both of them. Okay, for mountain, for Savannah to match together. All right, so that we can able to test our experiment. So let's print the for this one now. You can print you have 64 for this mean, and if you supply for this also, you can see that they are different. Okay, that one is also 64.60. This is 4 points. So let's we can conclude that if you run this, if you now test now, let's run the test now. This is our test. We have passed our data match here, our Savannah match here. So we just passed the pair equal to true. No, the formal pair was false before, so we can run now. We have 0.06, which is not significant. All right. So which seems that it is not equal to 0. So we can conclude that there is a weak evidence to suggest a difference in mean weight between animals from the mountain and the Savannah Island. Okay. So that's it. So in the next class, we'll continue there by looking at other tests, which we are going to continue later. So for now, this is just a sample t-test, and I will see you in the next in part 2 of this test. Thank you.